Good morning, everyone. It's truly amazing. We experienced sub-frigid weather last week, and now it's nice and warm, and we're turning the AC back on. So it's one of those things where we know we live in Texas, and we get all kinds of weather. So I hope everybody is getting back into a solid routine, as I said on Tuesday. Now, one thing I just wanted to mention, uh, it takes me quite a while to go through your test, and what I have you do, which many of you did very well, you take your Blackboard test, you receive a grade. Then you submit your test work, and I check the timestamps, and the majority of you adhere to the 30-minute rule, and I appreciate that. And so what I do, and this might be a source of confusion, but it shouldn't be. You're STEM professionals. When you submit your test work, I go to your Blackboard test, and I look through all of your answers, and I earmark the ones that you missed. So I've got those. I make a sheet for everybody, and I write it down, and I go to your test work. And not only do I look at the problems you missed, I look at the problems you got correct. And so I look through those to make sure that your work is there. Now, if you do a problem correctly and you show your work, it doesn't take very long to figure out the logic is there. That's fine. Now, the ones that you miss, I look at those, I scan those a little with more detail. And usually what the case is that there's a major logic flaw. Okay, so if that's the case, you're not going to get any credit for that problem. So the test work is not extra credit. So very rarely are you going to get any partial credit unless it's just a minor glitch. Because a math problem requires many facets and major logic flaws, like including a solution that doesn't even make sense in the original equation, is a major flaw. So if you get a grade of 0, if you look at the note I leave you, that says that your partial credit was 0. That is, on the problems you missed, you received no additional points. So that's good. You did exactly what I asked you to do. Say if student John makes an 85, and I check the problems that he misses, and there's no credit, there are major flaws in all 3 problems, then he keeps his grade as long as the support is there for the other problems. And so that's good. So if you have a 0 and student John gets his 85, then that's excellent. Okay. In rare cases, there will be an awarding of partial credit points, but it's very rare. And then, of course, if your work does not support your answers, then there is a negative score. Now, I was very lenient the first time that I graded. For instance, if you in your test work just write down an answer, you write an equation and write down an answer, there's no work, there's no logic, there's no definition of variables, that is not showing support, and that's a wrong answer. So in the future, if you're already doing your work like you should be, everything's fine. So don't look at a grade of 0. Really, I guess we transcend from test work to partial credit, but I'm not going to change the column titles. You should understand by the note that I leave you what the intention of that grade is. So I don't want there to be any confusion. Your test work is support for the work that you do on the test. It is not a source of extra credit. It is a necessary component of a test. And I appreciate the fact that many of you did excellent test work. There are 2 or 3 people in this class, and you know by what comments I left you, I said excellent work. And I want to see your work, so I appreciate that. It's important that you show me what you're doing. I have a few students say, well, I solved this with a graphing calculator. Guess how many points they got for that? They got negative points. So I do not solve problems with graphing calculators. You can use your calculator to do some basic arithmetic, which is fine. But unless we need Google to get a nice approximation, calculus approximation. We do all of our work by hand. We show an exact solution. So I'm very grateful for the majority of you that followed those rules. So I just don't want there to be any confusion about that. I take my grading very seriously, and I spend quite a bit of time studying your papers. So I don't want to be insulted by emails that try to contradict what I'm saying. I am very straightforward when what I ask you to do. The test tests you on the material that I've taught you, and they are extremely fair. So please continue doing what I ask you to do. And as you work hard through this class, you will be prepared for the calculus sequence, which is the goal. Okay, so now what we want to do is talk more about the logarithms. Now, where were we? Well, we know a logarithm is a power of the base. So what we wanted to do, and I promised you last week, is to go through some of the identities that the logarithms possess, and then see how those actually impact solving equations. So when we think about a logarithm, we think about the fact that its inverse has wonderful, wonderful exponential identity properties, the laws of exponents. So we're looking to find the counterparts with the inverse function called the logarithm. So this will be 4.4, and I'll bleed in today to the next section, which I've already uploaded on WebAssign 4.5. So basically, logarithm identities. Nice, interesting word, logarithm identities. And then we'll also talk about some equations. So here's the theorem. So first, what we're going to do, we're going to take a couple of bases. So let A, B be bases. Remember, bases are positive numbers that aren't unity. R will be a real number, any real number, and X and Y will be positive real numbers, greater than 0. So it's like we're doing inequalities, which you all are good at doing. And I want to also say, those of you that follow the techniques that I have taught have moved your level of thinking up. And I would call out some of you individually, but you know, by the notes I left, I was very impressed with the work in some cases. I definitely know that you all are going places. So I appreciate your hard work. Now, the very first one is going to be what we call the product rule. Now, of course, when you get into calculus, there'll be another product rule. And so you're going to have a lot of things called the product rule. Unfortunately, in English, we just run out of ways to describe things. So this will be the base A logarithm of a product. Notice in a lot of cases, when we've got a product, it's unambiguous about the actual input. So if you want to put parentheses here, like WebAssign usually asks you to do, that's fine. But a product is unambiguous because we're taking the base A logarithm of XY. And this will be the sum of the logarithms. That is, we can basically break up the product X times Y into two pieces and apply the logarithm. So this looks like an exponential rule. So again, you know, when you raise A to the X to the Y power, you multiply the X and the Y. So, and then of course, if that's the power rule, and if you do, for instance, you do something like this, A to the X times A to the Y, this is A to the X plus Y. So I'll kind of write down what this is actually mimicking here as we move through. Now, 2 will be the quotient rule, and these are at least fairly simple to justify using our logarithm as a power of the base rule, which is all we can do before we get to calculus. So you're thinking now, what about a quotient? And I'll go ahead and use parentheses just to be very clear. You're thinking this is just a special case of the product rule because we could always write 1 over y is y to the negative 1. But that's okay. We'll go ahead and write this down. The base A logarithm of x minus the base A logarithm of y. So we would say that the log of the quotient is the difference of logs. And then we look at the product rule and say that the log of the product is the sum of logs. So we might think of this like this. All right. And number 3 will be the power rule. The very last one will just be change of base. It's kind of off to the side, but I want to include it because it's an important property of the logarithms. Being able to change the base is something we establish in pre-cal. And as we move to calculus, there'll be no other adjustment to it. It'll be fine the way it is. So we'll say the base A logarithm of a power function or an exponential. The base can vary or not. So if we say the base A logarithm of x raised to the r, we can actually move the power r to a coefficient of the logarithm. And this is called the power rule, so to speak. So this is kind of mimicking this rule. When we raise things to powers, we just multiply. So this one is one of those power rules that we think are identities that surprise us but don't surprise us, because when we think of a logarithm being an actual power, an exponent of the base, then these properties make sense. But it makes the logarithm very special, very special. And just like the determinant in linear algebra, we're stuck with them. Theoretically, we need them, even if we don't always find their utility to be as high as other things. But no need to give a function a bad rap. We'll always use logs and exponents as we move through the calculus sequence. And then, of course, as you move on to the university with your engineering classes and whatever part of the STEM field that you happen to enter. And now number 4 will be change of base. So it might be convenient if we're solving an equation. For instance, you're thinking if we have 2 different bases, in order to solve the equation, we would need to have a single base. So it would be very important to know how to change it if indeed we can. So we'll say the base A logarithm of x. We want to change to base B. So we'll just say the base B logarithm of x. That's just cosmetic, divided by the base B logarithm of the previous base. So the thing is that I promise you, I didn't make this up. It's so easy to remember that there's certain things about logarithms that are really good. Now, the idea is if we're thinking about being able to solve equations using the fact, again, I want to just go ahead and write down, I'm going to write this in red. This is our little rule that kind of tells us what a logarithm is. That is y equals the base A logarithm of x. And of course, the x must be positive. That's why I've notated this restriction here. If and only if x equals a to the y. A logarithm is the unique power of the base. So again, the base A logarithm of x is the power of a that actually equals x, the power of the base. Okay, so again, this definition, even though it is somewhat intuitive just based on how we define the exponential, is extremely important. When we get to calculus, we'll see that this meshes with the integral definition of the natural log, even though at first I'd always have students in the past, it's like, I don't believe this. This is crazy. And I agree with them. It's very odd. So what we're doing is kind of like trigonometry. We take an approach that's going to push us into the realm of using logs and exponents, just like it's going to be the way when we do sines and cosines. We're focusing on a more intuitive way to substantiate them. And then, of course, as you learn more math, you can think of differing ways to define these functions. However, these concepts here will help us to solve important equations in math and science, whereas a more abstract definition wouldn't. So we think of just adding layers to our knowledge as we move through the classes, as we gain closer and closer approximation to our degree. So again, some of you may do the Bachelor of Science degree, and others of you may go on to the Master of Science or the PhD. You certainly have plenty of ability, and there's, as I've always said, my boss is really good about this. I remember one time he told a student, and I completely agree. He says, if you want to go on and take more education, do it. Don't stop. Because we stop our education and then we get used to a new life and don't want to go back. So that's excellent advice. Or if you're like Professor Ron, you can wait a long time and then go back to Texas A&M. But I agree with my boss that's a tough way to go, because you basically have to reinvent yourself. But to each his own. So now let's look at this particular identity here and justify it given our nice little definition of the logarithm. So for number one, I just want you to see that these actually are justified based on how we've defined the logarithm. Of course, assuming, and I know this sounds circular, assuming the laws of exponents. In calculus, we won't have to be this untoward and use the circular arguments, but right now this is all we can do. So we'll relish the fact that we at least have something to do. So what we want to do first is use this mechanism here. So basically what we're going to do is let, in this case, and we're looking at these things right here. So we're going to let z equal the base a logarithm of x, and just so we can use this little rule here, and we'll let W, or omega, your favorite letter, right? Or Professor Ron's favorite letter, especially in calculus, would be the base A logarithm of Y. So what we want to be able to do is do the transaction that we have right here. A logarithm is a power of the base. So again, the power of A that equals X is Z. So we can use our rule to say that X equals a to the z, okay? And now, again, we can use the rule again. The power of a that equals y is w, so y equals a to the w, okay? So again, these are all guaranteed if we can assume what we know about the exponential functions and their nice identities. So now, so this implies we can now look at the actual product of x and y, which we need right here. So we follow what we're supposed to prove in ways that will get us to the finish line. So x times y will just be a to the z times a to the w. And of course, now we go up here to the laws of exponents and we can add the exponents. We see the addition, right? So a to the z plus w. Now, I want to show you that we actually have this again. So xy equals a to the z plus w. But notice, z plus w is a power of the base, so it's a logarithm. So the power of a that equals xy is z plus w. So equivalently, z plus w equals the base a logarithm of xy. But now, of course, z and w are the logs that we need, so we just fill everything in. So we have base a logarithm of x plus base a logarithm of y equals the base a logarithm of xy, right there. So like I said before, if we assume that we have knowledge of the exponential functions, we can use our definition basically, which is just the reverse path. You know, we think about what a function does, the exponential, and we're reversing the path. We're having to figure out the power. So this intuition is actually extremely beneficial. And so now we see that it really is part of the fabric of these functions, that this rule would exist because that one exists. Okay, so what I want you to do, just like I tell my Calculus 2 students when we do reduction formulas for trig integrals with integration by parts, I say, okay, put all these formulas on a note card because they're going to save you time. Here, put these on a note card, write them down, commit them to memory, understand them, but do not force yourself to write them incorrectly. So always have them available for you to peruse. Okay, so again, think of these as tools to help us do greater and greater things. Now, one thing that I want to say a little bit about, and we'll say more about it as we get a little bit more practice. If you want to go ahead and try to prove these with a similar technique, you should go ahead. It's very straightforward. I will say more about change of base when we get to it and justify that. But now you kind of have the roadmap of what you can do. Now you're thinking, what can we do with these logarithm identities? Well, noting here that we have a condensed or compressed deal, that is a single argument, we can expand. So when we go from the single term to two terms, that's an expansion. And then, of course, this power rule allows us to move coefficients into the power of the argument. So we can use these identities to expand an expression, which is great in calculus. Or if we're solving equations, we can use these identities to combine or compress. So we end up with one logarithm. Remember, and this is very important, to use this rule, we must only have one logarithm. We can't just kind of apply the rule here and then go to another part of the equation and apply the rule again. That would not make any sense. So when we solve equations, we're going to want to combine. When we're taking derivatives in calculus, we're going to want to expand. So let's practice each of those techniques. And then we're going to look at the change of base and start solving some equations. So again, what these identities are going to do for you is to help you understand the objects even better. So here's an example. In this case, let's expand. For this example, expand. And we have the logarithm of x cubed y to the fourth divided by z to the sixth. So we'll start out with a simple one. So expand using log identities. So now when we look at this and we're thinking, okay, well, so maybe, and again, I apologize, we've got three variables here. This isn't a calculus 3 class, but just look at this as academic. Maybe I'll do an example where we have just one variable, which will be like an equation solving technique. But here, just look at this as an academic exercise, maybe not really going anywhere except until when you get to calculus. So for instance, notice here, we have the log of a quotient. So we can take the difference of logs. Now remember, LOG without a subscript means base 10. Remember, 10 is a distinguished base, and we have a unique way of denoting it. Put the 10 there if you want, but no, if it's absent, then it is intended to be the base 10. So by the quotient rule, we'll have log of x cubed y to the fourth minus base 10 log, and I'll put the parentheses in just to be a little bit more clear. Clearly, this is unambiguous without them, but WebAssign always asks you to close the parentheses, so that's fine, and there's no issue in it. If you get tired of it, you can leave them out as long as it's clear what your intentions are. Now, notice, we can attack each of these separately. Notice here we have a product, and here we've got the power rule, which we'll eventually have to apply here. So now think of this, and if you like, just go ahead and put a little dot right there to remind you that that's a product. So we want to apply the product rule to the first term to break it up into a sum. So this will be the base 10 log of x cubed plus the base 10 log of y to the fourth. So that takes care of this, at least in as much as we can do in one step. And then here, of course, we have the z raised to a power. That's the power rule. So the 6 can become a coefficient. So we're going to bring the 6 down. So 6 base 10 log of z. And what I will say here is write, just to be clear, write all powers as coefficients. Bring them down so they actually multiply the logarithm, just to be clear, just to kind of break it down completely. So now we look at this term and say, well, that's about as simple as we can make it. Now, of course, we can now apply the the power rule to both of these terms. So let's do that. So this will be 3 base 10 log of x plus 4, bring the 4 down to become a coefficient, log of y, base 10 log of y, minus 6 times the base 10 log of z. Now remember, this is just like saying 3 times the square root of 2. Square root of 2 is a number, and to multiply it, we just put the 3 to the side of it by juxtaposition. Here, this is the base 10 log of z, whatever that is. I mean, if we're given a value of z, we could give a specific answer, but this is multiplying the base 10 logarithm of z by 6. What is log of z? It's the power of 10 that equals z. That's a number or a variable depending on what we're actually doing. So again, we're multiplying an expression or number by another number, just like saying 3 times the square root of 2 or whatever. So now notice this is decomposed, this is expanded. So when you get to calculus and you're doing derivatives of log expressions, you're probably going to say, I'm going to break this up and apply the derivative of the logarithm to each of the terms and make my life a lot easier. So there will be applications of this, even though we won't use it as much in this class, but still we will have opportunities in the future to make more use of it. So there's always a reason to learn something. It's just that we don't always use it for each problem and it gets rusty. Now, I have another example here that just before we do the combining ones that I thought was very interesting. This I found in your ebook. So we want to expand this, and this reminds me of calculus problems, but it's certainly very doable if we use the laws of exponents. So this is a very interesting example. The one thing I've told many times to my students, there are many calculus and pre-calculus books, but the Stewart book has excellent rigor, at least as far as I can tolerate, and good examples, just like the Larson calculus text. So what makes you better is that you practice a lot of good, interesting problems. Now, if we want to expand this, it would probably be much easier to convert all of these radicals to their algebraic equivalent 1/2 powers. So let's do that first. So we're going to do x and then y, z to the 1/2. Now 1/2, or the square root of the product, y times z to the 1/2, and then of course the square root of the whole thing. So when you look at this, you're thinking, okay, so the outer square root is really the power 1/2. The inner square root, again, the power 1/2, and the most inner square root, power 1/2. So of course, even if you did not do this problem as I'm doing it, if you apply the rules of the logarithm and the exponents correctly, the same answer will ensue. Again, it doesn't matter. It's just like when I look at your test work, you got the problem right and you did a time, rate, distance, bam, 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 bam. I can see your logic, click. So the thing about math is that even though I'll look at your examples and I'll see your work and you'll have differing approaches, it doesn't matter. It all works out. So now what we want to do is now apply the laws of exponents to this object. So we can just take each of these powers and raise to the 1/2 and use the laws of exponents. So let's go ahead and break it down some more. So now we're going to apply the 1/2 to x. And then we're going to have, let me go ahead and write it this way so it's clear. We have y, z to the 1/2, applying the 1/2. So we apply the 1/2 to each of these, and let's just keep going. So log x to the 1/2. And now notice, in this particular case, when we look at this, we've got in the inside here, notice, and this is very important. When we apply the 1/2 here, notice these multiply. So we get y z to the 1/2 raised to the 1/4. So again, 1/2 times 1/2 is 1/4. 1/2 times 1 is 1/2. Okay, let's keep going. So you're thinking, if we didn't do this, we could still apply another approach, which would still work. Now let's apply the power rule one more time. So we get x to the 1/2, and then we get y to the 1/4, and then we get 1/4 times 1/2, which is 1/8. Okay? So now when you look at this, and it's very important, we see that we have reduced this argument to just a product of 3 expressions. And you're thinking, oh, can we use the product rule? Absolutely. For instance, you can think we could apply it to x to the 1/2 times this part and then break this part down, or just do it all at once. So we can apply the product rule in two factors, and then break down the other factors. So let's just say we're being very academic here. So we'll think of this factor times this factor. So apply the product rule. So this will be log of x to the 1/2 plus log of y to the 1/4 z to the 1/8. And so now you're thinking, oh, very good. Power rule, 1/2 log of x. And now here, apply the product rule, which we could have broken all 3 down and just written it out, but we'll do it step by step, plus base 10 log y to the 1/4 plus base 10 log z to the 1/8. This is fun. A lot of times, you know, I always say math is not fun. It's only fun when you understand it. But I have to look at this and say, this is somewhat fun. It's an academic exercise, but it is kind of like a little puzzle, not too tedious, but interesting. And so now power rule. So 1/2 log of x plus 1/4 base 10 log of y plus 1/8 base 10 log of z. Now, the idea here, and it doesn't really matter how you actually do this. I just thought it would be interesting to affect the solution using all the bells and whistles that we can. This is certainly not the most efficient way to do it, because I've added a lot of ideas here. But let's see here. Okay. Oh, hello, everybody. So now notice, again, if you were trying, if these were all expressions in x, this would be difficult in calculus to differentiate, but these sums here would be much simpler. So like I say, there won't be the realization of how important this is until you get to calculus. And of course, at the end of calculus 1, you introduce the natural logarithm. And then of course that parlays into the natural exponential, and then of course all the other bases. So just like I said on Tuesday, the natural base is the base of calculus, like pi is the basically the number of Euclidean geometry. Okay, so without pi, we would be hard pressed to do Euclidean geometry, and without base e, the natural base, we would be hard pressed to do calculus. So the key here is just applying the rules over and over, and then of course a careful utilization of the laws of exponents. Okay, Stephen, be sure to turn your mic off. I'm getting feedback from your room, so be sure to turn your mic off, please. Now, let's go ahead and use some other ideas. That is, for instance, if we can expand, let's go ahead and compress. So here's an example. So for instance, maybe we're solving an equation. So we have something like this. We have 4. Now, I'm not discriminating against other log bases. I'm just using base 10 since it's simple. We could have base 2 or base 3. It wouldn't matter. The log properties work for any base. So base 10 of x minus 1/3 base 10 log of x squared plus 1 plus 2 log of x minus 1. So now what we want to do is combine into one logarithm term. So when we look at this, we're thinking, okay, this might be a technique that would be useful if we were trying to solve an equation, whereas we've got a lot of log terms and we want to combine them, okay? So now what we want to do is say, all right, if we want to combine terms, we have to move the coefficients into the power status. Because note, and this is very important, these particular rules basically require that the coefficients of the logs be 1. And so when we move this way, we can do that. We can combine as long as the coefficient of the log term is 1. Okay, so that's really important. And we don't want to change that. So now, first thing we want to do is move all of the powers, in this case, all these coefficients into the power status. So this will be log x to the 4th. Now at this point, you're thinking, do we move the 1/3 with the negative, or do we just move the 1/3? We can use either. So let's just go ahead and move the whole number, the negative 1/3, and then we'll just basically reciprocate that. So this will be plus base 10 log x squared plus 1 to the negative 1/3. Just take the whole number, no problem. That's easier to deal with. And then we can move the 2 into the power. Okay, so when we look at these particular techniques, we're thinking, okay, the log identities, it's like a two-way street, just like doing the algebraic identities with the factoring. We can factor, we can combine. So it really just depends what the problem is asking us to do. So now we can look at these and just pair these off in 2. We can apply the product rule here and then apply the product rule here. Now, first, one thing we might want to do is go ahead and move this downstairs, but if we don't, we can do it later. So this will be the log of x to the 4th times x squared plus 1 to the negative 1/3. So again, we have the 2 arguments, which now we can multiply and write one log term, plus log of x minus 1 quantity squared. Now again, we're down to 2 log terms. So you can do this by 2s. Do it systematically by 2s. And maybe you had started with these 2. It wouldn't matter. And if it did, we'd be in trouble. So again, the consistency here just relies upon the fact that we use standard operating procedure in mathematics. So now we can say the product of this times this. So we have the logarithm of x to the fourth, x squared plus 1 to the negative 1/3, and then x minus 1 quantity squared. Now, of course, you might think, well, we can just go ahead and move this downstairs to get rid of the negative power, but this is certainly correct. But just to make it a little bit cleaner, let's get rid of the negative power. So we have x to the fourth, x minus 1 quantity squared, and then downstairs we have x squared plus 1 to the 1/3, right there. Now, you look at these problems and say, well, if we did this, we could just take it backwards. So when you do a problem, you can run it in reverse and practice the other procedure. Okay, so the idea is that we'll say good for solving equations, especially if we have more than one log term. It would be certainly very beneficial to combine them and then apply the definition of the logarithm. Just remember that we can't apply the definition of a logarithm in an equation if we have more than one log term. It doesn't make any sense. Now again, the combining process is fairly straightforward. And like I say, just use the examples in WebAssign just to practice with the basic construct. There are lots of simple examples that'll give you very good reinforcement. And that's really why I like the WebAssign. It forces you to practice the fundamentals, because the fundamentals are what get us where we want to go. Now, let's look at a very simple little lemma. I pulled this right out of your ebook in the logarithm chapter. And then, of course, we're going to say a little bit about change of base. But I thought this was a good example using the properties of the logarithm. So here we go. Okay, now, again, everybody, be sure your mic is turned off. I notice a lot of you have your mics on, and I'm getting feedback. So please turn your mic off, because it distracts me while I'm teaching. So Stephen and Christian, please turn your mics off, please. Now, in this particular case, we want to prove the following: that the negative of the natural log of x minus the square root of x squared minus 1 equals the natural log of x plus the square root of x squared minus 1. Now, when you look at this, you're thinking, okay, well, we just learned the power rule. And when we think about the power rule, we think about moving the coefficients up to the power status. And then we're thinking, okay, what can we do with that? Well, we've used a conjugate method before, and it's actually proven to be very useful. We're going to find that it's very useful when we do trig. But this is a good example of this, because when we get to trig, we're going to hit everything many times with conjugates. So I want to do another example of this. So what we're going to do is start with this side and show that it's equivalent to this side. So let's do it. So we're just going to say, here's our proof. So first we start out with the negative log of x minus the square root of x squared minus 1. Now, the first thing we want to do is, again, move the power, the minus 1, here. This particular coefficient becomes a power by the power rule. So we have natural log of x minus the square root of x squared minus 1 raised to the minus 1 power. Now, when we look at this, we're thinking, okay, well, this is fine, but to work with it algebraically, let's go ahead and get rid of the negative 1 like we did in the previous exercise. That's why I did that example, so we could, again, retire the negative power. So this will be the log of 1 divided by x minus the square root of x squared minus 1. So if you like, you can think of this way. Now, when we look at this and we look at that, we're thinking this is what we're going to be doing in trig, and we say, well, not so sure that this actually equals that or is equivalent to it. So this is where we can take the conjugate method. That is to multiply by the sum of x and the square root of x squared minus 1, like thinking complex conjugate, where we change the plus to a minus or a minus to a plus. So let's do that. So now, you can write in red, use conjugate method. Conjugate method. So we're going to multiply and divide by the sum of this. Again, we're not changing the expression, we're rewriting it, which is, gosh, that's math, right? We do it all the time. So we have 1 x minus the square root of x squared minus 1. And then if you like, we can just go ahead and do this in another color. This will be x plus the square root of x squared minus 1 and x plus the square root of x squared minus 1. Now, just to be careful here, remember we've got binomials here, so go ahead and put in your parentheses. Now you're thinking, there's what we need right there, so this part must be 1. So when we multiply it out, we're almost already home. So now we can see that again, what we have here and what we have here parallels. So let's do the arithmetic in the denominators. So we have natural log. So we have x, well, 1 times anything is just the anything, right? So we have x squared minus 1. And then downstairs, notice we have a difference of 2 squares. That's what's nice about the conjugate method. Notice we have x times the radical and negative x times the radical. So the outer and the inner terms absorb. That's always the case of the difference of 2 squares. Remember, if we have a minus b times a plus b, that just gives us a squared minus b squared. The inner and the outer terms absorb. So let's apply this here. So this will be x times x, which is x squared, and then minus the square of the radical, x squared minus 1 quantity squared. So we have natural log x plus the square root of x squared minus 1. And then, of course, when we square the radical, we remove the radical, and this gives us x squared minus x squared minus 1. And now we can reduce the denominator even more and get what we need. So again, if we distribute the negative, we have x squared minus x squared, that's 0, and we have negative negative, so we get our plus 1. So these absorb. And so we get our 1, and that's exactly, so this is exactly that. So why is this important? Why do we care? Well, if you probably haven't taken university physics, because you have to be in calculus 2 to take that, but the idea is that when you do engineering mathematics, sciences, engineering classes and things, just like you have all of these neat expressions, and you're thinking, well, I got this. I don't even know if these are the same. You'll be in a calculus class and your friend works a problem and you work it, and you stare at each other's responses and think, well, one of us did it wrong, when actually you both did the problem correctly. The thing is that you're going to realize in mathematics is that functions that have the same derivative differ by a constant. And that's the result of the mean value theorem. And so the idea is that you work with trig functions, you work with log functions, and you get these strange answers that, like, don't look equivalent, but when you work with them like we did here, you see, boom, these are equivalent. So again, what's an identity? An identity is an equation that is true for all values of the variables for which it is defined. And so this is an identity. The log identities we've been working with, again, they are valid as long as they're defined. Okay, when they're undefined, we don't even know what we have. But the idea is that these types of equations give us flexibility. And so we want to start thinking this way, because when we get to trig, everything's going to be an identity pretty much. We're going to move this expression to look like this. We're going to move this expression to look like this, just like what we do when we work with algebraic objects. It's the same thing. It's just with the trig and the log functions, we seem to have more of it. Now, I wanted to share with you an example having to do with change of base, and then we want to do an application from your WebAssign. So, change of base. What's interesting about the change of base is that you might be in a science class and you just need to change the base to do a computation, or maybe you're in a math class and you've got two different bases and you want to equalize them. That is, you want the same base so you can solve an equation. So there are many uses for change of base. The beauty of the change of base is that it does not in any way change the mathematics. It just makes the computation maybe more convenient for you. So now, remember, we have the base A logarithm of x, and we want to change to base B. So we have base B logarithm of x divided by the base B logarithm of the old base A. So when we look at this, we're thinking, wow, that again, it looks like magic is more than mathematics, maybe smoke and mirrors. But the idea is when we move from here to here, this is just a matter of doing a cosmetic change. That is changing A to B. And then the coefficient downstairs is what actually activates the change of base. That is, we take the base B logarithm of this base. So this is the change of base factor. Now, one thing that's really important in calculus is that we will always want to change our bases to base E to make sure that we can use the calculus. So here's an example. For instance, if we have a base 10 logarithm x and we want to change to base E, we'll just do log base E of x divided by log base E of 10. Now, when you look at that, you're like, well, Professor Ron, we don't do that. We don't, that's base 10 because there's no 10, there's no subscript there, but we have a different notation for log base E, and that's ln. So we would just say ln of x divided by ln of 10. Okay, so this would be what we will spend a lot of time doing in calculus. That is, if we want to change from base 10 to base E, we just do this. Or in general, if we just have the base A logarithm of x, this will just be the natural log of x divided by the natural log of the base A. So this would be a mechanism for changing any base to the natural base, which is the base of calculus. Base of calculus. The idea is that if I give you all this information, I need to show you how you're going to be using it. Otherwise, I think all we're just doing is problems that don't seem to go anywhere. So the key about the pre-calculus course is to look at what all these objects are and how they're going to impact you when you get to calculus. So you're going to be very busy changing base A to base E. And then we will know the calculus of base E, and that will allow us to move all the problems forward when it comes to derivatives and integrals. So here's an interesting example that I have for you. I want you to simplify the following. we'll hold off on a justification of this to give you a little break. So I want to simplify log base 2 of 5 times log base 5 of 7. Now, when you look at this, you think, okay, sure. What do these mean? This is log base 2 of 5. This is the power of 2 that equals 5. What's the logarithm? Power of the base. This is the power of 5 that equals 7. Now, if we notice here and we look at this, we see, for instance, we would know where this would live. For instance, 2 squared equals 4, and 5 is bigger than 4, and of course less than 8, which is 2 to the third. So we would know this number would live between 2 and 3, the power of the base here, if we went to our Google calculator to get a calculus approximation. Now the same here, we could say, all right, well, what about here? Well, base 5, 5 to the first power equals 5. 5 is certainly less than 7. And then, of course, 25, which is 5 squared. So then we would know this number would live between 1 and 2 and possibly closer to 1, since 7 is a lot less than 25. So the idea is that the logarithm is the power of the base. It's the unique power of the base. In this case, the power of 5 that actually equals 7, and we know it's between 1 and 2. The power of 5 that actually equals, power of 2 that equals 5, and we know it's between 2 and 3. So again, we can always guesstimate or get a good reasonable estimate of where the actual logarithm should live. And so when we go to the Google calculator and we get a nice estimate, calculus estimate, we say, yeah, that makes sense. That makes sense. Because again, as you do your problems, you're always looking, it's like, well, I got this number, but it doesn't look right. I'm doing an application. So we always have our intuition kick in, just like we've been doing with the time, rate, distance, or the fraction of work, or the mixture problems. So what you can do here, and this is something that students always like. It's like, well, maybe I can simplify this without having to do any further arithmetic by just changing the base. So here's a trick. Change to base 2. Change to, notice here we have the argument 5 and the base 5. That's what makes these work. Change to base 2. This one. So now we have log base 2 of 5. And now we're going to use the change of base. So we're going to change to base 2. So this is going to be log base 2 of 7. And this will be log base 2 of the old base 5. But now you see that these two numbers, they're real numbers, they absorb. And this gives you the base 2 logarithm of 7. So the key here, and this again is how you set up the argument and the base. You could string along a bunch of log terms where you go argument base, argument base, argument base, and this will happen. That is, as you change to this base, all of the terms will absorb except the very last one. So this is a way you can manipulate certain identities and theorems in mathematics to actually produce some interesting results. Because like I say, when it comes to changing the base, you may just want to change the base to do a computation, or you want to change the base for a theoretical construct. That is, if we want to simplify this, we could certainly figure out what they were with a calculator, but it's an approximation. It's not exact, so it's really not a proof, and not how I teach at all. We want to be able to use an approximation when it helps us finish the problem. Like we get to we're doing radioactive decay, and we want to figure out, how old is this artifact, like we did in the previous class. And then we go to that Google calculator, get a nice calculus approximation, and get a ballpark figure. That's a good use of our computing devices, and they are miraculous because they take the arithmetic of calculus and basically say, here you go. Here's a nice approximation that you didn't have to spend 10 minutes doing with a log table. Well, not 10 minutes, but I'm just saying back in the day before the calculators, we had tables. And of course, when I was a kid, we had calculators, but the teachers would always throw out the tables and we'd look in the old books. I remember my brother had an old math book from his college days, and I look in the back and it had just a bunch of tables in it. And I thought, yeah, that was the old way to do it. But the old way was actually good because everybody knew what a logarithm was. So now what we want to do, and here's something you might want to try. I'm going to go back to this just once you all have had a little bit of time to let all this sink in, and we'll talk about why this is true. But use this formula in the WebAssign. There's some real simple examples where you use the formula to get an approximation, and think about this, what I've done here, how we can actually use the change of base to simplify, just as a way of illuminating the power of the change of base. So again, be sure to put this in your notes. So when you get to calculus, you look in your book and you'll see exactly why this is very important. So again, this construct will not change. All of this will be the same when you get to calculus. Now, what we want to do is look at an application. And then we'll head to our equations. Here's an interesting example, kind of like the artifact example we did last class. So we're going to say that M corresponds to the magnitude of a star. Magnitude of a star. And for you scientists, it just really depends what, when you think of magnitude, like some kind of arithmetic component that talks about its size, the magnitude, maybe there's a number that says, okay, the magnitude is this for this star. And then we're going to say B will be a number that gives us the brightness of the star. Brightness of the star. And I'll just say the of the star and brightness of the star. And similarly, well, we always need constants like we had the D sub 0. B sub 0 will just be a positive constant that the astronomers figured out. Positive constant. Now, here's what the astronomers figured out. Just like the physicists, they do their field work, and they postulate a formula. And here's the formula that they got. They said the magnitude of the star, or of a star in general. So here you can just think A or it doesn't matter. I'll just say in general, A is good. It's going to be the negative 5/2 of the base 10 log of the brightness of the star divided by the constant B sub 0. Now, here's the interesting thing about this. The magnitude is a function of the brightness. Of course, we could go backwards and solve for B, but the magnitude is a function of the brightness tied up with a base 10 logarithm. And so we're thinking, all right, that was kind of the same thing we had with the age of the artifact with the negative and the log. I mean, it's the same thing. So let's just look at this and be able to prove something based upon this. So now here's what we're going to do. We have two stars. So we have star one that has brightness 1 and magnitude 1. And we have star 2, yeah, keep it really simple, right? Star 2, brightness 2, and magnitude 2. So you've got these components for each one. And so here's what you want to show. So we want to prove the following. And this is written up in your WebAssign. Prove if the brightness of B1 is less than the brightness of the brightness of star 1 is less than the brightness of star 2, B1 less than B2, then this applies in this case, that the magnitudes flip. The magnitude of star 1 is greater than the magnitude of star 2. So you're thinking, all right, well, doable, because we can always build this. We can start with this and build those formulas. Okay, so let's do it. So here's the proof. And this is maybe the easiest one we've done today. So we have B1 is less than B2. Now, what we want to do is just build this formula on each side of the equation. So what we're going to do is start with dividing both sides by the positive constant B0. So divide by B0, which of course doesn't change anything, nice and positive. And now when we look at this, we think, okay, we need to apply the logarithm next. The logarithm is a nice increasing function, the base 10 logarithm. So it will preserve the inequality. So now we want to apply the base 10 logarithm. So log of B1 divided by B sub 0 is less than log of B2 divided by B0. Again, remember, we've talked about this before. When you apply an increasing function to the inequality, it preserves it because the function is increasing. So this preserves. And now we look up here and say, okay, well, we're almost done. Let's just do the -5/2 in one swoop. So we'll just do one technique here. So now to get the formula, we have to multiply both sides by -5/2. But the idea, the number is less than 0, so the inequality will reverse. So now we have -5/2 log B1 divided by B0. Now switch, reverse, greater than -5/2 log B2 divided by B0. So now we've built the magnitude formulas for both sides of the equation. Now, of course, this by definition is M1, and this by definition is M2, and that's exactly what we wanted to show. So though this is very simple, like I said, easy, what's important here is we keep using the same ideas we've had before. If we apply an increasing function, it preserves the inequality. If we multiply an inequality by a negative number, a number less than 0, it reverses it. So we're using what we already knew. It's just now, since we know something about the logarithm, we can utilize this formula and now show a very interesting relationship between brightness and magnitude of stars. Now, of course, this is what I was talking about. When you study science, when you study engineering, the mathematics is the language, and you see formulas, and you have to be able to manipulate the formulas. And lots of times your professors will come in, okay, well, let's just show that this expression equals this expression. And so when you do science and engineering and computer science, the majority of what you do is mathematics. So I guess if you major in mathematics, you just really like the math completely. But most mathematicians, most math professors have particular parts of the discipline that they like more. And then there might be certain applications that they enjoy. So if you become a computer scientist or an electrical engineer or a financier or whatever, you're still going to be taking a lot of math along with you. And for instance, some of you may be, like I said before, some of you may become electrical engineers and work on the Texas electrical grid. So the thing is that there's all kinds of uses for mathematics. So here's a nice use of that. Now, I don't have too many students that tell me they want to become physicists or astronomers, but that is certainly a fascinating subject or discipline, and plenty of good schools to study that. Now, what I want to do is talk about some equations. Now, when it comes to solving equations, we basically have a couple of things that are useful to us. That is, we have the definition of the logarithm, and we have all these nice rules of exponents and identities of the logs that help us to adjust things if we need. So, solving equations. Now, when you think about solving equations, like I said before, you can start simple and you can move into more advanced. But let's look, I've got several examples here. To say I have several examples is an understatement. I can never seem to find enough problems, examples to exhaust. So let's start out with one that's exponential. So we'll just say solve in R. So we're going to have the following. This is right out of your WebAssign in your ebook. We have 125 raised to, in this case, the x power plus 5 raised to the 3x plus 1 power equals 200. Now, the idea here is that we have certain properties that are important. For instance, we know that the base A exponential is 1-to-1 and the base A logarithm is 1-to-1. So let me just remind you, we have 1-to-1 properties, just like we have the inverse equations, 1-to-1 properties. That is, number one, and we'll assume these are well defined. We'll say A to the U equals A to the V by 1-to-1 implies that U equals V. Likewise, again, assuming well defined, the base A logarithm of U equals the base A logarithm of V implies U equals V. Again, by 1-to-1. Remember, 1-to-1 says that if you have components in the range that are equal, then it must be the case that their inputs were equal. So the idea is that if we have a logarithm equal to a logarithm of the same base, we can just set the arguments equal. If we have an exponential function equal to an exponential function like this, we could set the powers equal. So there's simple ways to solve equations that basically just appeal to our common sense. And so we don't want to look at these as being difficult. We're thinking we just undo them with the inverse function, and then we can isolate the U and the V in both cases. So when we look at this problem, first we're thinking exponents. So we want to rewrite some of these powers here using the laws of exponents. And note, there's one big observation here, which you already see. 125 is 5 to the third power. That's kind of an important observation. So now let's do that. So we're going to say 5 to the third for 125 is raised to the x power using the laws of exponents eventually. And here we're going to say 5 to the 3x times 5 to the 1 using, again, the laws of exponents. Okay? So now we're like, oh, well, look at that. That's the same thing right here. This is just 5 to the 3x. So we'll go ahead and use the laws of exponents. 5 to the 3x, and I'm just going to put a 1 out here. And then, of course, this is plus 5 times 5 to the 3x. Just put the coefficient of 5 off to the left. And this equals what? 200. Now, what's nice about this equation is even though when you look at it initially, it looks really difficult, but it's not. We solved a simple equation last class using the definition of log. And now we look at this, we have 5 copies of 5 to the 3x, and we have 1 copy. So that gives us 6 copies. So 6 copies of 5 to the 3x equals 200. So the idea here is when we're trying to solve equations, maybe we get lucky and it's quadratic in an exponential or quadratic in a log and we can factor or use the quadratic formula. but usually we're really happy when we can distill it down to one expression in X, one logarithm or one exponential, because that way we can apply the definition of logarithm. We can go forwards or backwards. Without that, we're kind of stymied, so to speak. Now, we have a number times an exponential. So let's divide both sides by that number. And notice equivalently, this will be 5 to the 3x. And of course, we know that this is 2 times 3, and 200 is 2 times 100, right? So let's do some symbolic computation. Divide by 6, 2 times 3, and notice the 2's absorb, and this gives us 100 over 3. Now let me just go ahead and write the equation without the computation in the middle so you can easily see what we have. Now, when you look at this, you say, okay, what does this equation mean? Well, we have 5 to the 3x equals 100 over 3. 3x is a power of the base, so 3x is a logarithm. What is it? It's the base 5 logarithm of 100 over 3. So equivalently, using the definition of logarithm, what's a logarithm? Power of the base. 3x equals the base 5 logarithm of 100 divided by 3. So when you look at this and you think about our mechanism defining the logarithm, we use it all the time because the definition of the logarithm allows us to toggle between the exponential form and the logarithm form, back and forth, depending on what the equation asks us to do. And so now we've got this number here. What is this? This is the power of 5 that equals 100 over 3. And then to solve for x, we just have to divide that number by 3. So equivalently, x equals 1/3 of this, or we can just write 3 downstairs, base 5 logarithm of 100 over 3 divided by 3. And there's our number. Now we look at this and say, okay, well, the exponential functions are defined for all real numbers. That's a real number. So that's a bona fide solution, just like we always have to check. See, that's an egregious error. If you solve an equation and you don't even bother to think about what you've done, and you just say, oh, well, both of these are solutions. Well, no, that's a major logic flaw. We can't just say, well, I got a value of X, it must do something. Well, maybe it doesn't do anything, you know? Just because we're asked to solve an equation doesn't mean it has a solution. And then, of course, if we get several values of the variable, we have to make sure they actually make sense. That's a logic flaw. And that's what I saw a lot on the first test. So you need to be careful about that. I mean, if you're working at a LyondellBasell and you do a computation and you move your work forward with errors in it, then that may cause a major catastrophe or it may cause a problem. That's why you'll have 3 or 4 people look at your work to check it out. Everybody checks it out. Everybody checks the work. Unfortunately, when you do a test, you're the only one doing it. But that's the key. That's the key to successful workmanship when it comes to doing a STEM job. Because just like when I was an undergraduate, when I was a volunteer in the emergency room, all the doctors and the nurses would compare notes. They'd say, well, this is what I'm going to do. I want you to check this. Or a nurse would come up and mix some medicines and they say, Ron, did I do these proportions right? And I say, well, I'll check it. I said, it looks good. And then I pass it along to someone else. Oh, it looks good. And then we complete the procedure. So the idea is that the math is important and we have to make sure we push forward mathematics that actually solves the problem and doesn't hinder it. So now we can go over here to our solution set or just say this is bona fide and say the base 5 logarithm of 100 over 3 divided by 3 is a definite solution. So again, this focuses on the fact that when we solve an equation, we use the identities. We use the laws of exponents. We use the log identities. And then we use the definition of the logarithm. What's a logarithm? It's a power of the base. And so that pushes us forward depending on which way we have to toggle with the actual mechanism. Now, I wanted to try one that's actually quadratic. this particular example, it kind of looks quadratic. I've talked about situations where, for instance, if you're trying to solve an equation and you want to rewrite it, and you don't want to necessarily introduce ideas that are wrong, but sometimes when you adjust an equation, maybe with a conjugate method or something, you can open the door to solutions. And then you say, wait a minute, look, now we've got these values of X. Do they work in the original? Jackpot. So here's an example of that. So example, this again is from your ebook, e to the X plus 15 e to the negative X. It's like I do in calculus. If I don't like the problem, I'll change it up. Usually it turns out that I'll change it up to make it more challenging or make it more interesting. I think what's important is that every problem should provide you with a new technique or provide you with something that you didn't know before. That's how we get better in mathematics. Sometimes it's really odd when I sit down to write my lecture notes, even if I've taught the class before, I'll say, you know what, I'm going to use this procedure. I'm going to focus on this because in the past, I felt that students had a more tough time with this topic. So I'm going to focus more on it. And so hopefully by the end of the section, there'll be a greater understanding. So again, what we want to try to do is move our thinking up a level. Even though I know all of this is review, it's still, we want to just be able to think a little bit deeper about these topics. Now, if you look at this problem here, you're keeping your fingers crossed that there are three terms that this is quadratic. And you're thinking you could retire the negative power downstairs and do a common denominator and get the same thing. So what I'm going to suggest, which will do the same, is just to multiply the equation by e to the X and see how that transforms it. So we want to create quadratic in e to the X. So here I'm going to suggest multiply, which is what this negative power suggests, multiply by e to the X, transform. So let's do it. So we're going to have e to the X times e to the X. We're going to use our laws of exponents plus 15 e to the negative X times e to the X minus 8 times e to the X. And of course, 0 times anything is 0. So I'll just stick it there, but you know, it's just 0. We didn't leave out the 0 or think that it was unimportant. It just annihilates everything. When you get to calculus and the lower limit annihilates the integrand, you're like, yay, that's less work to do. Adding 0 or subtracting 0 is always very quick process, right? So now when you look at this, notice, let's just do a little aside, e to the negative X times e to the X is just e to the 0 when we add the powers. And of course, by definition, that's just 1. So we see that we just get a 15 times 1 or a 15 here using, again, the laws of exponents and how we define the base to the 0 power. So now we're like, okay, 2 plus 2 or x plus x, 1 plus 1 is 2, sorry, e to the 2x plus, now we have 15 times a 1 minus 8 e to the x equals 0. Now, of course, if you can look at this, let's go ahead and rearrange this. We have e to the x quantity squared minus 8 times e to the x plus 15 equals 0. Now, this is exactly what I said before, and I wrote this way so you can see now that we have a constant term, we have the so-called first degree term, and then we have the squared term. So now you're thinking, okay, I see this, Professor Ron. This is quadratic in e to the x. So let's write that down. Quadratic in e to the x. And so now we keep our fingers crossed. The harder problem would be that this wouldn't factor, but you can see with AC, this is going to factor. So we've got a 1 here. So AC equals 15. So we want to get the -8. So we'll just use a -3 and a -5. And that's so simple because again, the leading coefficient is 1. So we clearly see this works with Professor Ron's AC lemma. So now we have what? E to the x minus 3, e to the x minus 5. So again, just remember, with the equations I ask you to solve, there will be a technique to allow you to get to a solution, okay? When you get to calculus, you're gonna learn a procedure called Newton's method, or I'll do the rolling D or the passing D, passing T, Newton's method, if we're gonna speak correct English. The idea is that you will be introduced to a technique that will allow you to approximate certain solutions when an actual closed form solution will be very difficult. And that will be something that some of you all will use in your future engineering classes. And of course, as you take engineering classes with my colleague, Nate Wiggins, who does engineering, and he's very good. So you're going to enjoy those classes. So he will actually introduce these topics to you. And the thing is, that's fine once you have the calculus background. But right now we're going to focus on equations that you can actually solve with the techniques I give you. Now, when you look at this, we have zero product. So now this says if and only if e to the x minus 3 equals 0, or e to the x minus 5 equals 0. I just don't want you to think that I'm going to ask you to solve equations that won't have solutions that you can get to. I won't do that to you. So now we can just set these up as standard exponentials. So e to the x equals 3, or e to the x equals 5. So now when we look at this, again, we use the definition of logarithm. X is a power of the base. So X is the base E logarithm of 3. X is a power of the base. So X is the base E logarithm of 5, but we don't do base E, we just do ln. So equivalently, using definition of logarithm, X equals ln 3, or X equals ln 5. Now, when you look at this, again, these are real numbers, and these make perfect sense in the original equation. Remember, the exponential functions are very, very user-friendly. Okay, they're defined for all reals unless the powers get kind of interesting, and then probably we couldn't solve the equation anyway. The key here is that if we don't have an exponential equal an exponential where we can set the powers equal, we need to figure out some pattern that we recognize. Is it just a matter of condensing the problem down to one exponential, or is it a matter of recognizing that this is actually a quadratic equation? And then, of course, if it's quadratic, we do this because we know how to solve it. Okay. The key is, and I say this often to my calculus students, we look for patterns in mathematics. We look for patterns because the patterns tell us what we can do next. If we don't find the pattern, then we lack a technique. So you have to stare at it a little bit longer. Maybe we're solving a word problem. Maybe I didn't set this up right, or maybe I didn't read this correctly, okay? So now these both work here in the original, so we do have bona fide solutions. Natural log of 3, natural log of 5. Now, a lot of times in WebAssign, they'll ask you to type the exact answer, and then you can use your Google calculator. Usually on the next line, they'll say approximate to 2 decimals or 3 decimals. So you can use your Google calculator with base E to approximate these. I kind of like that because you do the exact answer, and then you kind of help out your client and say, okay, well, this is a decimal approximation. If you're working at the bank and you say, well, your monthly payment's going to be, $150 or something. So that way they can budget. Okay. Now let's look at some other examples. What I wanted to do now is use the condensation process. That is the combining process, because when you have logarithms, just like with exponentials, we want to be able to reduce down to one log term. So let's try one of those. So here we go. We want to solve in the real numbers. So we say solve in R. So in this case, well, here we go. You won't believe it. I'm going to use base 9. So we have log base 9 of x minus 5 plus log base 9 of x plus 3. I usually try to make sure that the problems do what I want them to do. I've worked out problems before, and I'll say, well, kids, these equations do have solutions, but I would make them too interesting. And then of course they're like, well, are we actually going to solve an equation that has an answer? And I said, yeah, let me do that. Let me be a less creative. So now when we look at this, we see we've got the base 9 logarithm of x minus 5 plus the base 9 logarithm of x plus 3 equals 1. And when you look at that, you're thinking, okay, I can't use the definition of logarithm because I have two log terms, but no worries, right? This is the sum of logs. The coefficients here are ones, so we can bring these together using the product rule. So combine using the product rule. Again, we have a 1 here, a 1 here. So this will be the base 9 logarithm of x minus 5 times x plus 3. And you can just, put extra parentheses if you want, just to make it clear, equals 1. So again, we've already taken this problem to the next level because now we've got one log term, which is critical for solving log equations. So now let's go ahead and write this out. Base 9 logarithm, what are we going to get? X squared. And now, of course, we have a 3x minus a 5x. That's a negative 2x. Really simple. When we did those time, rate, distance problems, we had more algebra and arithmetic than we wanted. And of course, my poor calculus 2 students, center of mass and work, they've got all kinds of arithmetic, which they don't always like. And then, of course, the negative 15 equals 1. So you're thinking, all right, you might think, well, Professor Ron, why did you multiply that out? What I'm thinking about is that we're going to have this constant over here when we apply the definition of logarithm, and then we're going to have a quadratic. So if you got something factored plus a number, then you're going to have to undo it eventually. So I went ahead and multiplied it. Or if you don't have to, you can just do it later. Now we've got what we need. Again, the power of 9 that equals x squared minus 2x minus 15 is 1. So that's even easier. So 9 to the first power. So x squared minus 2x minus 15, write the exponential form, is 9 to the first power. What's the logarithm? Power of the base. So the power of 9 that equals this is 1. But what's 9 to the 1? That's 9. Okay. So now you see now that we can transform this equation and we have quadratic in x, which is kind of what we did, the very first week, right? So now if and only if x squared minus 2x, and of course we subtract 9 from 15, and that'll be a negative 25. So again, this is quadratic in x. The idea here is that it does not matter how often we see an equation type. We always identify it, even if it's like the last problem where it's quadratic in e to the x, because then that tells us exactly what we need to do. So of course, again, very nice condition here. We have AC equals, in this case, a negative 25. Oh, and now I'm sorry, ding, that's a 4. 9 plus 15 is 24. Very good. Because I was fixing to say that's not as nice as I thought it would be. So yeah, arithmetic does help. So we've got negative 24. And of course, now we can look at AC and use negative 6 and 4 because the sum will be negative 2. So again, when we think about why we do what we do and we think about writing our test work down, is because we always have a blueprint of what we're doing. And then boom, we can make sure that everything looks good. We can make sure that everything's consistent. Because again, when you look at this problem, what would make it harder? What would make it harder is that we had to use the quadratic formula, which again is doable. We've done it many times, but this is a much more quick solution because it does factor. And now equivalently, we can use the -6 and the 4 right here. So this will give us x minus 6 times x plus 4 equals 0. So now, zero product, if and only if x equals 6 or x equals -4. These are a lot easier because when we look at problems like this, we think, oh, with the logarithms and the exponentials, we've got to do a little bit more work. But this is commonplace. So now we've got these two values, just like we did before. We want to make sure that these are actually good in the original. But we see an issue with the -4 when we look at this particular term. The -4 will make this argument less than 0, and the base A logarithm is only defined for positive inputs. So this one we would have to discard. So discard, because that violates the domain of the base 9 logarithm. So now our solution set will be good here because, again, we can check we're good here. And of course, when you look at some of these problems, ladies and gentlemen, you can stare at them long enough and solve them in your head. But as I say many times, the key here is to work through the algebra to uncover all the solutions. So maybe you figure out one on your own, and then you just want to check to see, is there actually another one? So now we've got 6 and we're done. Now, when it comes to solving equations, we're also going to do some applications with some with interest and all. But I've got an example here that I thought was interesting that, again, alludes to some algebra that's useful. So let's look at another example. And then we have time, we'll go ahead and talk about the interest problem. Or I'll do that at the beginning of next lecture when we talk about Newton's law of cooling and radioactive decay and things like that. So here we go, example. Solve in R. So in this particular case, we've got a base 10 logarithm. We've got base 10 log of x cubed equals 3 times the log of x. So again, most equations that you're going to see will just be what you normally do. You isolate the object that has the variable, and then you undo it. Excuse me, using some technique that's valid. Now, when you look at this, we're thinking, well, isn't this interesting? But it's not difficult at all, because if we think of this as being 3 copies of log x that we have on the right-hand side, we see here that we have the cube of that. That is 3 copies here, but it's in a multiplicative sense. So you're thinking, we need to factor this because, again, the power rule doesn't work. This is the log, base 10 log of x raised to the 3rd power. It's not log of x cubed, which would mean power rule. So again, this is not the power rule. So I want you to mark in your notes, not power rule. Lots of times students see a log raised to a power and then they think, oh, I can just use the power rule. No, it's the argument raised to the power that allows you to move the power to the coefficient. But this is not power rule. This is a factoring problem. So I'll just say this is a factoring problem. So what I'm going to do is do what we always do. We can think of this as x cubed equals 3 times x. That's all we're doing. So again, think of this as just being a cubic equation in log x, just like we normally do. So we've got what? Log x cubed. So you could make a substitution, but I don't think it's necessary. That's just extra baggage. We substitute when we need to, and I'll show you how to do that in calculus. Now we're good to go. We can now factor this and produce the zero product. So now we can see we've got a log x term here and a log x term here, which we can easily factor. So log x times, again, you're thinking, can I use the cheap notation? I won't. We will do that in trig, but I'll avoid it here. I don't want to, a lot of times we can, if we're saying that the square of log x, we can put the 2 by the log like we're going to do in trig functions, but I'll avoid that for now because I don't normally do it. And it's not always considered to be standard. What I'm talking about is like later on, when we say cosine of x quantity squared, that's a whole lot of writing. So the shorthand is going to be cosine, put a 2 here, and that's going to mean that. That is when we say cosine superscript 2x, that's going to stand for cosine of x quantity squared. And this is so useful because we have to write so many powers of the trig functions that when we're writing it, this turns out to be a very nice, efficient shorthand. So I'm not going to do the same here. It's not standard. So now we can factor this. This is a difference of 2 squares. So if and only if we have log of x and we have base 10 log of x minus, again, we're going to write 3 as the square root of 3 squared, just a little smoke and mirrors. So square root 3 log x plus square root 3 equals 0. I mean, this is so natural because this is what we've done many, many times with our equation solving. Why do I always say factoring is essential? Because it is. I mean, factoring here is the necessary technique. So an inability to factor is an inability to solve a lot of mathematics. So now we can use zero product. So if and only if base 10 log of x equals 0, or we'll go ahead and solve this, base 10 log of x equals square root 3, or base 10 log of x equals the additive inverse or the negative of the square root of 3. Now again, when you look at this problem, you say, well, it's not so bad because it's just a pattern that you've solved many, many times. So again, as I tell my students in the calculus sequence and beyond, practice makes you better at the patterns. And when I look at your work, I can tell a lot of you practice, have an excellent work, very clean, very easy to read. So now we think, okay, we've got to use our mechanism that defines the logarithm. So again, it says the power of 10 that equals x is 0. So x equals 10 to the 0. Well, 10 to the 0 by definition is 1. Well, that was easy. Now it says the power of 10 that equals x is square root of 3. So x equals 10 to the square root of 3 power. Very interesting number. It exists. So that's the first time we've seen something like that in this course. 10 raised to the square root of 3. That's a bona fide number. And when you take more calculus, you'll learn even more about that. And lastly, x equals 10 to the negative 3rd power. So of course we could retire the negative and bring it downstairs, but it's good. Now notice, and this is very important here, 1, fine. This is a positive number, no problem. This is a positive number, no problem. So all of these get a check. I mean, we didn't square anything. All we did was factor. So we really had no opportunity to introduce extraneous zeros. We didn't do anything that would have brought them into fruition, so to speak. But it's always good just to do a little once over to make sure that everything is good. So now when we write our solution set, we have 1, 10 to the square root of 3, and 10 to the negative square root of 3. So what I want to do is just introduce some interesting problems along with the standard problems, just so you can see that this is just disguised version of something you already know how to solve. And that's That's what we do with quadratic form. We're so happy about quadratic form because we know it. And of course, we're happy about algebraic equations that have no constant term. We know the constant term is a thorn in our side. So we're trying to find zeros. We have to work a lot harder to find them. The rational zeros theorem will help us find rational zeros if they exist. But it's really hard to move a problem forward unless you have at least some way of getting attached to 1 0 so you can reduce the degree of the equation. Now let's try one more. Now, this next equation is something I wanted to talk about with the one-to-one property. And then we'll do that application of the interest on the next class, because I want to have time to say something about that. So here's the last example. And if you want to go ahead and jump into those, that's fine. But I think you all have plenty of work finishing up your examples that you have in your WebAssign. So like I say, today I've got 3 sessions, so feel free to come by and ask your questions. This is a long day, but I felt like as we get to the end of the week, you have questions and you have examples that you need to see. So I'll send out email invitations for those. So the last example, we want to solve in R. And this is, again, I'm not discriminating. It's just base 10 log. You put a 3 on it if you want. Base 10 log of X plus base 10 log of 3. Now, this actually is simpler than the last equation, but it looks a little bit odd. And so when we think about this, we're thinking, oh, this is going to be the one-to-one property. And if you look at this long enough, you could solve this in your head. But let's approach this with the mechanism like I asked for you to do on the test. If you just write down an answer for a mixture problem, then I can't really give you credit. I need to see your work. I need to see the execution of the variables and the execution of the algebraic logic, because this is a math class. Now, when you look at this, you're thinking, well, just like the last problem or previous problems, we can combine these 2 log terms into 1 log term. So equivalently, we have log of X plus 3, which doesn't change, equals log, then we'll just do 3 times X. So this is a similar circumstance like we might have with exponentials. And I'll do some examples with some more exponentials and all that will allow us to kind of flex our logarithm muscle, so to speak. When we don't have the same base, we can't set the arguments equal. And so if you've got different bases with log terms or different bases with exponential terms, then you've got to change the base. And that's going to make the terms a little bit more complicated looking, but it will allow you to use the one-to-one property. So notice here, the one-to-one property is valid because we have the base 10 logarithm of X plus 3 equals the base 10 logarithm of 3X. So we can use one-to-one. Note, we've got the same base for both log terms. That's important. So now equivalently, X plus 3 equals 3X. Well, don't we wish all equations were this easy? So we'll subtract X from both sides. 2X equals 3. And so X will be 3 over 2. And so now, of course, you can easily see that these are well defined for these log terms, and we have a solution. So again, when you look at these problems, I don't want you to be careless, but I don't want you to be afraid of them either. So again, as is necessary, and I'll say a little bit more about this, we may need to change the base because of the convenience of utilizing one-to-one. So I'll just say same base so we can use one-to-one property. So many ideas in mathematics depend on having the proper circumstance. And so now, like I say, we could have stared at this for a while and maybe come up with 3/2. But what we're seeing is that even though this term is fixed, we can't really do anything with it. We can combine these two terms. And then you're thinking, well, we've got two log terms, but it's okay. They're set equal. We can use 1-to-1. We don't have anything in the way. Or we could think about maybe subtracting a log from both terms side and then using like the quotient rule, but that would be overkill. So when we look at these examples, what I want you to do is think about the laws of exponents. I want you to think about the laws of logarithms and how they mesh together and how we use, what's our main mechanism here? Y equals the base A logarithm of X if and only if X is equal to A to the Y. So this is the mechanism that ties together the exponential function and the log function. Okay, so like I said before, I will send out some invitations today for the office hours or the conference hours. So be sure to take advantage of those and enjoy the what do they call it? The warm weather that we're having. I have no idea what the forecast is going to hold. But thanks for your attention today, and thanks for your attendance. I hope everybody's doing better, and I'll see you soon.